Welcome back to Neural Intel, everyone. Today, we're doing a real deep dive into something that honestly might surprise you quite a bit, especially if you follow AI closely.
That's right. We're talking about running these incredibly powerful large language models,
The
LLMs.
big ones.
Yeah,
But running them right here, directly on your personal Apple Silicon Mac.
exactly. And for ages, the thinking has always been you need massive cloud setups for this stuff.
Or, super specialized, power-hungry hardware that costs a fortune.
Right. That's been the standard view.
But that reality seems to be shifting, and pretty dramatically. It turns out your everyday Mac might actually be this quiet powerhouse just waiting to be unleashed for AI.
It's absolutely true. The whole landscape for deploying AI is changing, like fundamentally.
So our mission today on Neural Intel is to really pull back the curtain. We want to unpack the technical innovations, the tools, the software stacks that are making this local AI thing not just possible.
But actually, astonishingly efficient, especially on Apple's M series chips, the M1, M2, M3, M4.
We're going to dig into the why. Why would you, our listener, even want to do this?
And crucially, the how. What's the clever engineering, the software magic making it work so well?
Our goal is that by the end of this deep dive, you'll have those key technical nuggets. You'll really understand the landscape and maybe even feel equipped to try it yourself.
And remember, for all the specific papers, code repositories, or tools we mention, check out the links on our webpage that's in the bio. We're keeping the focus squarely on the tech today.
Absolutely. And for this, we've cast a wide net source-wise. We've looked at guides for specific frameworks like Llama.cpp.
Which was a real pioneer.
Definitely. And deep dives into optimized stacks like Apple's own MLX.
Plus, really valuable stuff from user experiences, people sharing what actually works on forums and communities.
So by the time we're done, you should have a really clear picture of the tech, the tools, and how it all fits together for local LLMs on your Mac. Ready to dive in?
Let's do it.
Okay, so let's kick things off. Most of us, when we think LLMs, we think ChatGPT, Claude, Gemini, cloud services, right? Accessed via an API.
That's the common experience, yeah.
So why should you, sitting there with your Mac, even care about running these big models locally? Isn't the cloud just easier? What's the actual draw beyond it being kind of cool?
That's a fair question, and the sources we looked at point to some really compelling technical reasons. I mean, reasons that go way beyond just novelty.
Okay, like what?
First, and this is probably the biggest one for many, privacy and control. Think about it. When you use a cloud LLM,
Your data goes up to their servers.
exactly, it leaves your device, travels over the internet, gets processed on hardware you don't own or manage, and then the result comes back.
Which raises all sorts of questions.
Right. Running it locally. Your data, your notes, your business plans, your private chats, it never leaves your machine. Period.
That's huge. It basically eliminates that whole third-party exposure risk.
Completely. And that's massive if you're dealing with sensitive information or regulatory stuff like GDPR or APA. Compliance becomes way easier.
Okay, privacy is a killer app right there.
Yeah.
But what about the practicalities? Cloud APIs seem pretty cheap to get started with, don't they?
They often have low initial barriers, yeah.
Yeah.
But that's where the second big advantage comes in, cost efficiency.
The hidden costs.
Well, they're not always hidden, but they are recurring. Cloud usage means paying for compute time, storage, maybe token counts. It adds up, especially with heavy use.
Right.
Locally, once you have the hardware your Mac, the operational cost for running inference for actually using the model is essentially zero, no recurring fees.
So it lowers the bar for just playing around, experimenting, developing.
Massively. For students, indie developers, small research teams, it makes serious AI experimentation accessible without needing a big budget or worrying about runaway cloud bills. You're not paying per query.
That really does feel like democratizing access, doesn't it? Making powerful AI available to more people.
It absolutely does. And there's more. Think about reduced overhead.
Meaning,
You don't have to mess with remote APIs, authentication keys, network latency issues, managing cloud infrastructure.
it's just running on your machine.
Exactly.
Yeah.
The whole stack is right there.
Yeah.
Simpler development, faster iteration. And then there's the obvious one, offline operation.
Yeah, no internet, no problem.
Right. On a plane, out in the field, network outage, your local LLM just keeps working. That's critical for some applications where you just can't rely on connectivity.
Okay, those are genuinely strong arguments. Privacy, cost, simplicity, offline use. But this all sounds great if the hardware can handle it.
Yeah.
LLMs are beasts computationally.
They are, traditionally, yes.
So this is where Apple Silicon, the M-series chips, becomes the linchpin, right? The sources position them as a real game changer for local AI. What's the magic? What's the technical secret sauce?
The M chips really are a different beast architecturally, and that difference is perfect for AI. The biggest deal is the Unified Memory Architecture, or UMA.
Okay, explain UMA. How's it different from my old PC with a graphics card?
So in that traditional PC, your CPU has its main system RAM, right? And your separate graphics card, your GPU, has its own dedicated video RAM, VRAM.
Right. Two separate pools of memory.
Exactly. Now, LLMs need huge amounts of data. The model weights themselves, all the intermediate calculations, the activation.
And they need both the CPU and GPU to work on it.
Correct. So in that old system, data is constantly being copied back and forth between the system RAM and the GPU's VRAM across the PCIe bus.
Which I'm guessing is slow.
Relatively speaking, yes, it's a bottleneck. Especially for the massive data sets LLMs work with, this data shuffling really limits performance and dictates how much VRAM you must have.
Okay, so how does unified memory change that?
With UMA on Apple Silicon, the CPU and the GPU and the neural engine too actually all share the exact same pool of physical memory.
Ah, so no more copying data back and forth.
Precisely. They can both access the same data directly, simultaneously. It dramatically reduces latency. That data transfer bottleneck just evaporates.
And that means?
It means two crucial things. One, it's faster. But two, and maybe more importantly, it allows much larger models to fit and run efficiently. A model that might demand, say, 24 gigs of dedicated VRAM on a PC GPU.
Might run fine on a Mac with just 16 or 32 gigs of unified memory.
Exactly, because that memory is used so much more efficiently, there's no duplication, and access is incredibly fast for all the processing units. It fundamentally changes the memory calculus for these large models.
That's a really fundamental architectural shift, almost rethinking how the computer works internally. What else about Apple Silicon makes it good for AI? Is it just the memory?
No, not just the memory. It also packs powerful acceleration hardware right onto the chip. The big one is the integrated neural engine.
Okay, what's that?
It's basically specialized silicon. Cores designed specifically for the types of math operations that dominate machine learning, especially neural networks, things like matrix multiplies.
So not general-purpose CPU cores trying to do AI math, but dedicated hardware.
Exactly. Custom built for the job. And this neural engine, combined with Apple's Metal backend, that's their low-level graphics and compute API, provides direct hardware-accelerated pathways for AI tasks.
So faster computations.
Much faster, and crucially, much more power efficient than doing the same work on the CPU or even sometimes a traditional discrete GPU.
Right, efficiency. That's the other piece people always talk about with M chips. How does this all tie together for the user experience? What do you actually feel?
It translates into remarkable efficiency. You've got the CPU, GPU, neural engine, all tightly integrated on one chip, all sharing that super fast unified memory.
Okay.
This means you get really high performance, but at way lower power consumption compared to traditional setups.
Which means my MacBook doesn't sound like it's about to take off when I run an LLM.
Pretty much. You can run surprisingly large models without the fan screaming, without your battery draining in 20 minutes. It makes local AI genuinely practical on a laptop, even a thin and light one. That portability, combined with the power, is what's enabling this shift.
It really is fascinating. A hardware foundation perfectly suited for this kind of workload. But hardware is only half the story, right? You need the software to take advantage of it.
Absolutely. And that's where things got really interesting, especially with open source projects.
Which brings us neatly to Llama.cpp. Our sources call it a significant advancement, a gateway to cutting-edge AI. It feels like this project really kicked the door open for many people.
What is Llama.cpp?
Llama.cpp is, well, it's kind of legendary in the local LLM space now. Developed by Georgy Gerganov.
Yeah.
At its heart, it's a very efficient C++ implementation specifically for the Llama model architecture family.
C++eng, okay. But what makes it a gateway? What was so special about its approach?
Its core innovation, the thing that made everyone sit up and notice, was its CPU-first design.
So unlike the big frameworks that basically required a hefty GPU.
Exactly. So many frameworks were built assuming you had powerful, dedicated GPUs with lots of VRAM. Llama.cpp was engineered from the ground up to run really well on just standard CPUs.
Which most people actually have in their computers. Precisely. It democratized access. Suddenly, you didn't need a multi-thousand-dollar AI workstation. You could run a pretty sophisticated LLM on your existing laptop or desktop. That was huge.
And being C++ probably helped with getting it onto different machines.
Definitely. That CC++ foundation gives it incredible portability. It compiles and runs smoothly across Linux, macOS, Windows, basically anywhere you have a C++ compiler. Super versatile.
So the key benefits boiling down to efficiency, especially on CPUs.
Portability across platforms.
And I imagine the open source nature helped too.
Massively. It has a hugely vibrant open source community that means constant updates, bug fixes, support for new models almost as soon as they appear, optimizations. It moves incredibly fast because so many people are contributing. That community energy is a major advantage.
Okay, that explains why it took off. But let's get a bit more technical. You said it's an efficient C++ implementation. What specific architectural tricks or adaptations did Gergenoff use? How did he make it run so well, especially compared to maybe more standard transformer models? What's under the hood?
This is where the clever engineering really comes in. Llama.cpp isn't just a straight port. It incorporates some really smart choices different from many standard transformer implementations.
Okay, like what?
One key thing is its use of pre-normalization. A lot of traditional transformers use post-normalization. They normalize the output of each layer. Llama.cpp often normalizes the input instead.
And why does that matter?
It uses a specific efficient normalization technique called RMS norm. The combination pre-normalization with RMS norm tends to improve training stability and overall model performance. For something designed to run on less powerful hardware, that stability is gold. Fewer resources needed, less likely to break.
Interesting. A subtle change in order with a big impact.
Right.
What about the core math bits, the activation functions?
Yeah, another change is the use of SWIGLU activation functions instead of the more common ReLU.
SWIGLU.
Okay.
What does that do?
It's a more complex activation function, but the research suggests it significantly enhances the model's ability to capture intricate patterns and relationships in the data. Basically, it lets the model learn richer representations, leading to better understanding and generation. It's a performance booster.
Got it. And language models need to understand word order, right? How does Llama.cpp handle positional information?
It uses rotary positional embeddings, or ROE.
Rope-E sounds cool. How's that different from just numbering words?
So simpler methods might just add a number based on the word's position. ROBE is more sophisticated. It essentially rotates the internal vector representations of words based on their position. Think of it like encoding relative position information directly into the vector's direction.
Okay. Why is that better?
It's particularly good at capturing relative distances and relationships between words, especially over longer sequences. Absolute positions can sometimes struggle with very long text. ROPE helps the model maintain a nuanced understanding of context and order, which is crucial for generating coherent text. These kinds of architectural tweaks are why Llama.cpp performs so well.
That's genuinely fascinating. Real engineering ingenuity there. Okay, so for someone listening thinking, I want to try this, how do you actually get Llama.cpp running on an M-series Mac? What's the practical process? Hardware requirements?
The great thing is the requirements are surprisingly modest. You mentioned a 7 billion parameter model earlier.
Yeah, 7B model. Sounds big.
Well, a quantized 7B model, we'll get to quantization in a sec, can often run with just 4 GB of RAM allocated to it.
Wow, really? So even a base Mac with 8 GB of unified memory could handle that?
Absolutely. It makes it super accessible. Now, the setup involves a few steps using the terminal, but they're pretty standard for developers.
Okay, walk us through it briefly.
First, you'll need Homebrew, the package manager for macOS. If you don't have it, you install it with a command from their website. Super easy. We'll link all these specific commands in the show notes, by the way.
Good old Homebrew, essential Mac tool. Then what?
Then you use Homebrew to install the prerequisites. CMake for building, Python, Git for version control, and RuGit for downloading. Just brew install, CMake Python, Git, RuGit.
Got it. Dependencies installed. Next,
you clone the llama.cpp repository from GitHub using git clone. Then you cd into the directory and just type make. That compiles the C++ code optimized for your Apple Silicon chip.
Okay, compiled. Now I need a brain for it, right? The actual LLM file.
Exactly. You need to download a model file. Hugging Face is the main place to find these. You'll often look for models in the gguf format, which is llama.cpp's preferred format.
GF. Okay, and you mentioned quantization.
Right. Many models you download will be quantized. This is a crucial technique. It reduces the model's size and computational needs by using lower precision numbers. Like instead of 16-bit floats, maybe 4-bit integers.
Which means it uses less RAM and runs faster.
Way less RAM, significantly faster. It's the magic that lets big models run on consumer hardware. Sometimes you download a pre-quantized GGOF model. Other times, you might download a higher precision model and use Llama.cpp's own tools to convert and quantize it yourself. There are scripts like convert.py and quantize in the Llama.cpp project for this.
Okay, so get the model, maybe quantize it, put it in the right folder.
Yeah.
Then what?
You'll usually need a Python environment, too, for some helper scripts. So you'd set up a virtual environment, Python 3-venvmv, activate it, and install requirements, pip install -r requirements.txt.
Standard Python practice. And finally, talking to the model.
Yep. Llama.cpp comes with example applications. You can run it in interactive chat mode using a command like main-m models your -model-file.gguf-p hello AI, or using their interactive chat script.
And you can tweak how it responds, right? You mentioned parameters earlier.
Absolutely. From the command line, you have lots of control.
Like what? Give us the key ones.
Okay. Model or nat-m obviously points to the model file. Prompt or nat-p is your input text.
Standard stuff.
Then you have npredict or nat-n, which limits the maximum number of tokens, words, subwords, in the response.
Controls length, got it.
Temp or temperature. This is really important. Lower values, like 0.1, make it very predictable, sticking to the most likely words. Higher values, like 0.8, make it more random, more creative, maybe more surprising.
The creativity dial.
Nice. Yeah. And top is another way to control randomness. It samples from the smallest set of words whose combined probability hits a certain threshold, helps avoid really weird outputs while keeping some diversity.
Temperature and tapa, the main knobs for tuning the output style.
Exactly. There are others like top K repetition penalties, but temp and tapa are the big ones for controlling the feel of the output. Llama.cpp gives you that fine-grained control.
That's great. It makes a powerful tool surprisingly flexible. Okay, Llama.cpp, fantastic CPU-first pioneer. But Apple wasn't going to just sit back, right? Enter MLX. Sources call it Apple's new open-source AML software stack, optimized specifically for Apple Silicon. This sounds like the next level up for performance on Macs.
That's exactly what MLX is designed to be. It's Apple's own framework built from the ground up to squeeze every last drop of performance out of their M-series chips.
So unlike Llama.cpp, which aims for broad compatibility, MLX is laser-focused on Apple hardware.
Precisely. Its entire reason for being is native optimization for Apple Silicon. It directly leverages the unified memory, the neural engine, and the Metal graphics and compute framework.
How is it structured? Is it just Swift or?
The core library is actually high-performance C++A for speed, but it provides APIs, front ends for both Python and Swift.
Okay, so accessible to both the huge Python ML community and native app developers.
Exactly. It aims to be, and the sources suggest it is, an extremely competitive choice for on-device AI on Macs, especially for inference actually running the models.
And it fully utilizes the GPU side through Metal.
Yes, that's key. Full GPU acceleration via Metal, making the most of that shared memory architecture we talked about. This often translates to significantly better performance than other frameworks can achieve on the same hardware.
Sounds very powerful. But like Llama.cpp, maybe a bit daunting for non-coders? This is where tools like LM Studio come in again, right?
Yeah.
How does LM Studio integrate this Apple native MLX?
LM Studio has been really smart about this. They've embraced MLX completely, offering first-class support. Meaning, starting around version 0.3.4, LM Studio actually ships with an MLX engine built in. You don't need to install MLX separately or fiddle with command lines to use it within LM Studio.
Oh, so it just works out of the box for MLX models.
Pretty much. It's designed for super efficient on-device LLMs using MLX right there in the familiar GUI. It makes MLX power incredibly accessible.
And this engine inside LM Studio, what's it made of? Is it also open source?
Yes. The MLX engine they use is open source, MIT licensed, which is great. It cleverly bundles together key Python components built on top of the core MLX library.
What?
It uses MLX-LM, which is Apple's own Python library for running language models with MLX. That's the core inference part.
Okay.
It also integrates Outlines, that library we mentioned for structure generation, making models output clean JSON, for example.
Right, the regex magic.
Exactly. And it includes MLX VLM for handling vision language models, the ones that can understand images.
That's quite a package. But interesting that they chose Python for this engine, not Swift, even though MLX supports Swift natively. Why Python?
It seems like a very pragmatic choice based on the sources. Two main reasons. First, community iteration. The Python AML community is just vast. Building the engine in Python lets them tap into that huge pool of developers for faster improvements, testing, and contributions.
Makes sense. Leverage the existing ecosystem.
Second, speed of support. New models, new research techniques, they almost always hit the Python ecosystem first. A Python engine means LM Studio can likely support the latest and greatest much faster than if they were waiting for Swift implementations.
So agility and community access trumped pure native implementation in this case.
It looks like it. And they built a clever technical solution using Python build standalone and stacked virtual environments to package it all neatly within LM Studio, avoiding making users download huge dependencies multiple times. It's quite sophisticated under the hood.
Very clever engineering. Okay, let's really pop the hood now on what this MLX engine does inside LM Studio. What advanced stuff can it handle? Starting with basic text generation using MLX LM.
All right, the core function is mlxlm.utils.generateStep. When you feed it a prompt, the model first runs its call method. This produces logits.
Logits again. The raw scores for every word in the vocabulary.
Exactly, a huge list of scores. These scores define a probability distribution, which word is most likely next, which is second most likely, and so on.
And then it picks one.
Then it samples a token, a word or subword, based on that distribution, using your parameters like temperature or top up to guide the choice. That chosen token is the next piece of the output, and the process repeats.
Simple enough conceptually. But what about forcing structure? You mentioned outlines in JSON. How does that actually work during generation?
This is where outlines integrated via a logits processor gets really cool. Remember that JSON schema example? Outlines turns that schema into a complex, regular expression.
Right.
Now, inside the generation loop, after the model produces the logits but before it samples the next token, the JSON logits processor steps in.
And does what?
It looks at the current state of the generated text and the rejects. Then it effectively masks the logits. It sets the probability of any token that would violate the rejects at that point to 0.
So it prunes the options, only allowing tokens that keep the output structurally valid according to the rejects.
Precisely. It forces the model down a path that must result in valid JSON or whatever structure the rejects defines. Then sampling happens only from the remaining valid tokens. It's incredibly powerful for reliable structured output.
That is seriously useful for practical applications.
Yeah.
Okay, what about images? You said MLX VLM handles vision models. How does that work, and can you combine it with the structured output?
Yes, LM Studio supports vision models like Elavia through LXVLM. The generate step function in MLXVLM is slightly different.
How so?
Well, its initial step has to process the actual image pixel data to feed into the model. Subsequent steps work more like the language model. Also, MLXVLM's native sampling options are a bit more limited, and critically, it doesn't directly accept a logits processor like the one Outlines uses.
Oh, so you can't directly ask a vision model for structured JSON output using the standard MLX VLM tools.
Not directly out of the box with MLXVLM alone, but LM Studio implemented a brilliant workaround, the Vision Model Wrapper class.
A wrapper. What does it wrap?
It cleverly wraps the MLXVLM model in a way that makes it compatible with the more feature-rich MLXLM.generateStep function.
So you use the text generation function with its advanced sampling and logits processing.
But you feed it the vision model via this wrapper. The wrapper handles the initial image processing, then passes control smoothly between the vision parts and the language parts, allowing MLXLM's features, including the JSON logits processor from Outlines, to work.
So you can give it an image and ask for a JSON description.
Exactly. You get the best of both worlds. Image understanding and reliable structured output. It's a really neat piece of engineering to bridge that gap.
That's fantastic. Combining modalities like that locally is really pushing the envelope. Now, one more critical optimization, conversational speed. Chatbots feel slow if they reread the whole history every time. You mentioned KV caching.
Yes, KV caching is absolutely essential for making chat interactions feel fluid. The problem is exactly that. Reprocessing the entire chat history on every single turn is computationally very expensive and slow.
Because most of the history hasn't changed.
Precisely. KV caching exploits the fact that inside the transformer model, many intermediate calculations, specifically the key and value matrices used in the attention mechanism for the past tokens, remain identical.
So you save them.
You save them in a KV cache.
Sure.
Then, when the next turn comes with new input, the model only needs to compute the keys and values for the new tokens. It reuses the cached ones for the entire preceding context.
Let's do that example again, quantum computing article summary.
Right. T1, summarize article. Engine computes KVs for the whole article, saves them. T2, LLM response. T3, you ask a follow-up. Any challenges mentioned.
Okay.
Without caching, the engine reprocesses the article summary and the first response and your new question. With caching, it loads the KVs for the summary and the first response from the cache, and only computes KVs for your new question. Any challenges mentioned.
So it only processes the new stuff?
Essentially, yes. It leverages the cache state for the past.
And the performance difference is significant.
Oh, it's night and day. The source mentioned a test processing a 3,000 token article with Llama.cpp. The first response took maybe 10 seconds, but a follow-up question using the KV cache.
How fast?
0.11 seconds.
Wow. From 10 seconds down to a tenth of a second for the follow-up.
Yep, that's the power of KV caching for conversational speed. It makes chatbots feel instant instead of sluggish.
That's incredible. How is it implemented in MLX within LM Studio?
MLX LM's generate step function has a cache history parameter. LM Studio's engine cleverly pre-fills this cache. It uses helper functions like process prompt and cache wrapper.update cache to process the initial prompt or existing chat history in chunks, say 512 tokens at a time, efficiently populating the KV cache.
Okay.
This populated cache history object is then passed into generate step for subsequent calls. The function automatically uses the cache, drastically reducing computation. You just need to make sure the cache tokens still match the start of your prompt each time.
The level of optimization is just, wow. It's not just raw chip power, it's incredibly smart software making it all sing.
Exactly. Hardware enables it, but software unlocks it.
Okay, we've gone deep into the engines, Llama.cpp, MLX. Let's pull back slightly and look at the tools that make this usable for everyday folks, and critically, how they perform head-to-head. LM Studio seems key here as that user-friendly gateway. What are its main user-facing strengths?
LM Studio's biggest win is definitely accessibility. Its GUI-based interface is huge, no command line needed. You download the app, point, click, search for models, download them, chat. It just lowers the barrier significantly.
Makes it approachable for non-devs or just people who prefer GUIs. What else?
The model exploration and management is really slick. Searching Hugging Face, seeing different versions, like different quantization levels, downloading. It's all integrated.
Easy discovery.
Yep. The interactive chat interface is clean and lets you tweak parameters like temperature on the fly. And for more advanced use, the local LLM server is fantastic.
The OpenAI compatible API.
Exactly. You can point other apps or your own scripts at LM Studio as if it were a cloud API. And it can even run multiple models at once, mixing Llama.cpp, GGUF, and MLX models. Super flexible.
That mixing ability is quite cool.
And the document chat.
Yeah, the document chat with RG is powerful. Load your PDFs, text files, whatever, and chat with your data locally.
Huge for privacy and personalized knowledge.
Plus the SDKs for developers.
Right, Python and TypeScript SDKs. And fundamentally, it's all built around offline operation. Privacy first.
Okay, LM Studio, the user-friendly, versatile choice. But there's another player, Llama, taking a very different Apple-native approach with Swift. Tell us about Llama.
Llama is really interesting because it's a pure Swift implementation, built directly on Apple's MLX framework, designed from the ground up for macOS and Apple Silicon. It aims for that deep native integration and performance.
So potentially even tighter integration than LM Studio's Python engine. What features does it offer?
It's got a really impressive feature set. Like LM Studio, it offers an OpenAI-compatible API chat completions, embeddings, even audio transcriptions, and it supports tool calling, which is quite advanced.
Cool calling locally. Nice.
Yeah. Interface-wise, it offers both a slick menu bar app for quick access and full command line tools for scripting and power users. Best of both worlds.
And capabilities. Multimodal.
Yep, multimodal support for text and images. A big one is local audio transcription using Whisper, built right in. No cloud needed to transcribe voice notes or meetings.
That's a killer feature for privacy.
Totally. It also does text embeddings locally for RA. Its smart model management is very convenient. Automatic downloads, caching, versioning, plus these handy aliases like Llama 3.2 or Whisper Large so you don't need long model names.
Aliases are nice.
Plus streaming responses for that real-time feel and direct Hugging Face integration. It's very polished and macOS native.
Sounds very capable. System requirements.
And how easy is the CLI to use?
Needs macOS 14 plus, Apple Silicon, building from source, Xcode 15 plus, and Swift 6.1 plus RSS 8. The CLI is designed for simplicity. After installing, you can just do Llama run quen 3 hi there to run a model with an alias. Llama list shows models. Llama serve starts the API server. Very straightforward.
Okay, two powerful tools, LM Studio and Llama, leveraging these underlying engines. Now for the big question, performance. How do MLX-optimized models stack up against the widely used GGUF models run via Llama.cpp on Apple Silicon? Is MLX actually faster in practice? The user reports and benchmarks we reviewed suggest, yes, there is a clear and significant performance advantage for MLX-optimized models on Apple Silicon.
Like, how much faster? Got numbers.
One specific user benchmark really stood out. They ran a fairly large model, Qwen3 30B, A3B, 30 billion parameters.
Okay, that's hefty for local.
Definitely.
Yeah.
With the MLX version, they were hitting 55 to 65 tokens per second.
That's flying for a 30B model locally.
It really is. Now, compare that to running the same model, but in the GGUF format using Llama.cpp implementations, like maybe an LM Studio or a Llama. They reported speeds around 35 tokens per second.
Wow. Okay, so 35 versus potentially 60 plus token sec, that's nearly double the speed for MLX in that case.
Exactly. It's a substantial difference, especially on larger models where the optimizations really pay off.
That's impressive raw speed.
Sure.
But you mentioned user experience earlier. Is it just about tokens per second, or does MLX feel better integrated too?
That's the other key point that came up. The same user reporting those speed differences also noted the system fluidity. They said that while running inference with MLX, the rest of macOS stayed perfectly smooth. Fluid macOS visual fluidity was the phrase. App switching, animations, multitasking with Stage Manager, all fine.
And with Llama.cpp GGUF.
They observed that sometimes Llama.cpp inference could cause the screen rendering or UI elements to stutter a bit, especially when multitasking heavily.
So while fast, it might impact the overall system responsiveness more.
It seems that way, at least in some scenarios. It suggests MLX's tighter integration with Metal, and the OS allows it to run these heavy tasks more gracefully without disrupting the user experience as much. It's not just faster, it feels more seamless.
That's a really important distinction. Raw speed plus system smoothness points to a significant advantage for the native MLX approach on Apple Silicon. Well, this has been a truly deep dive. We started with the why, privacy, cost control, making local LLMs compelling.
Then the how, Apple Silicon's unified memory and accelerators providing the hardware foundation.
We explored Llama.cp, the open-source C++ pioneer that made it accessible.
Highlighting its clever tricks like pre-normalization, SWGLU, and Ropey.
And then Apple's own MLX stack, optimized purely for their hardware, enabling that next level of performance.
We saw how tools like LM Studio make MLX accessible with advanced features like structured output via outlines, vision model support, and that crucial KV caching for conversational speed.
And we touched on Swama, the native Swift alternative, offering a highly integrated macOS experience.
Bringing it all together with performance numbers showing MLX delivering significant speedups and better system fluidity compared to GGUF Llama.cpp on these M-series Macs.
So the takeaway for you, our listener, is that you now hopefully have a much clearer picture of the tech involved, the architectures, the software, the optimizations.
And you know about the tools like LM Studio and Swama that let you actually harness this power yourself right on your Mac. The ability to run really capable AI locally is here now.
We absolutely encourage you to try it out. Grab LM Studio, maybe check out Swama, download a model that fits your Mac's RAM, and just experiment, see what's possible. All the links are on the Neural Intel page in the bio.
It's a fascinating space to explore.
And as we wrap up, here's a thought to leave you with. This shift towards powerful, efficient local AI, especially on optimized hardware like Apple Silicon, isn't just a technical curiosity. It fundamentally changes the game. How might application development change when developers can assume powerful AI capabilities are available right on the user's device without relying on the cloud?
Yeah, that opens up possibilities for apps that are more private, more responsive, more personalized.
Exactly. Are we moving towards a future where the most sophisticated AI doesn't just live in massive data centers but resides right at the edge, intimately woven into our personal devices? It feels like we're right on the cusp of that transformation.
A very exciting prospect indeed.